All right. So, before we get going here, kind of a recap. We'll pick up where we left off in Module 12. After class today, you'll see that 12th module quiz pop up here. You'll also see that top hat reading for Module 13. Those are both due at the end of the day on Monday. So after Monday next week, this is the last module reading we have, right? So that next week is the last week of new material we have. So once that due date passes, probably not until Tuesday, I'll update Canvas so that it drops your lowest module reading. I mentioned this back in the syllabus first week. And then after that kind of 13th module quiz, which won't be until the following week, once that's passed, I'll update Canvas so it drops your lowest quiz score. And then after next week, we have our last two in-class quizzes. Once we're done with those next Thursday, I'll update Canvas to drop your 4 lowest. Okay, so you'll start to see Canvas kind of get updated with those adjustments once we've gotten all the assignments complete in those different categories. Okay, so last module reading is this week. Last module quiz will be next week. Next week are the last 2 in-class quizzes that we have, because the following week will be the week before finals. We're not going to have class that Tuesday. So I'll post up a reminder announcement. I'm going to post up a video of me working through a lot of the questions in those practice exams, just like we would if we did have class. That Thursday, we will have class where you can kind of come in, ask questions that you have, but there won't be any in-class quizzes, right? There's no points for attending that day. It's just additional time for review for that final. And then that video I'll post to kind of replace that class on Tuesday will be me just kind of working through problems, practicing that final, okay? What's due at the end of the day tomorrow? That 4th Canvas discussion. The 5th Canvas discussion I'll post next week. It'll be due at the end of the week on Friday, that week before finals. So that should be, shouldn't be too terrible. I'll kind of have kind of a similar thing where we're using AI. I'll kind of talk more about that next week after I publish it, after Tuesday's class next week. Okay, so that's everything we have remaining for the rest of the semester. Other than that, any questions for me before we just dive into material here? Okay. So once again, CL sessions kind of as usual this week and next week as well. I'm still waiting on, I'm going to try to have a CL session that week before finals on Thursday to kind of replace that one day that we missed for, what was it? I don't even know, whatever schools canceled, whenever we had canceled, snow or whatever. So I'll kind of mention more about that as we get closer to that date, what those CL sessions look like. But otherwise, we'll kind of jump in where we left off. Okay. So last class, we were looking at all these normal form gain matrices, and we had some of these examples of prisoner's dilemmas, right? So the definition of our prisoner's dilemma is we end up in an equilibrium that makes both individuals worse off than if they could somehow agree to a different combination of strategy choices. So just some examples of this in the real world, and then we'll work through one more to kind of give a review of what we're doing last class. So ad wars, right? So if there's 2 companies and we don't run ads, we're maybe splitting demand evenly, right? We haven't had to spend any additional money. But if I'm the one company that runs ads, I can convince a lot more people to buy my product, so I can increase my profits and the profits of the other firm would decrease. Now, if we both run ads, maybe we still split demand, but we have these huge additional costs, which was all this money we had to dump into our marketing department. So this is an example where it's always going to have an incentive to be the one that does run ads when someone else doesn't. And so we end up with this Nash equilibrium where every company runs these ads, which are huge costs, which actually lower their profits. We end up in a Nash equilibrium where it's worse off than if we could both agree just to not run any ads. We talked about companies trying to set prices like a monopolist, or kind of like OPEC, like these cartels, we call them. They basically coordinate their actions to act like a monopolist. We said there's always this incentive to be the one firm that breaks that agreement and charge a lower price. So we ended up with this Nash equilibrium where we saw the companies both set lower prices closer to that perfectly competitive point, which was a bad thing for those firms, right? It had a prisoner's dilemma. However, it's a good thing for the market overall because we're moving closer to that perfectly competitive point. Same kind of idea with arms races, spending on not like ads, but spending on military defense. Think about all these countries, we dump all this money into our militaries. Well, we would be all better off if we could just agree to kind of live copacetic and like nobody has to spend any money on their military. But there's always an incentive to be the one firm that has nuclear weapons, because then I can make everybody else do what I want, right? So these are great examples of prisoners' dilemmas. And then they kind of connect some things to old topics we talked about. Common resources, and we'll maybe do a little review of this on some of those final exam practice questions. It's nothing new, it's just painted in a different context. Common resources also fall victim to this prisoner's dilemma, right? If we all are fishing a pond, we agree to only catch 2 fish. That's what's optimal for society. The problem is there's an incentive to be the one person who catches a couple of additional fish, right? But if we all have that incentive, we all catch a couple additional fish, the pond ends up being, right? We eliminate that fish population, nobody gets anything. So common resources are another example where we see this prisoner's dilemma pop out. And then we talked about last class, even though the prisoner's dilemma is a bad thing for the individuals involved, maybe it's a bad thing for firms because it ends up in having a quantity and price closer to that perfectly competitive point where we know profits will be equal to what? Perfectly competitive profits are 0 in the long run. So it's bad for the firms, but it's a good thing for the market because we're increasing total surplus. So when we talk about this prisoner's dilemma, it's a bad thing for the people that are involved in that game. It may not necessarily be a bad thing for the market or for society, right? So it's just the payoffs of the individuals in that game. So we'll kind of think about a different setup, right? So this isn't, thinking about economics. A lot of times we put this in context of markets, but we can also use game theory to understand individual decision-making, even in like political economy examples. So let's say I have 2 candidates and they both say, okay, we're not going to run negative attack ads against each other. We both kind of keep the same amount of votes. We haven't convinced any voters to like change their decision. Now, if we both run negative attack ads, right? So actually, sorry, I'll do the first one first. Let's say the Republican candidate runs a negative attack ad and it convinces some Democrats to not vote for their candidate. And it convinces them to vote for the Republican candidate instead, because they now hear all these bad things about the other candidate. Well, some people will switch their vote, and there's going to be some people who, I was going to vote Democratic. I saw these negative ads against the Democratic candidate. I don't want to vote for this person, but I also don't want to vote for the Republican. So I just don't vote at all. So kind of think about this scenario. If I'm the candidate who runs negative ads, but the other doesn't, I might gain some votes, and the other person is going to lose some votes. Right? So I think I chose the values of 1,000 and 3,000 here. And then if we both run negative ads, some people will change their mind, right? As long as they're equally efficient negative attack ads, maybe some people switch the candidate they're going to vote for, but then some people just don't vote at all. So usually I'm going to have this word problem. I wouldn't necessarily expect you to have to build the normal form game matrices with the payoffs. I'm just giving you some context behind why those payoffs would be what they are in class. I'd be more likely to show you the normal form game that looks like this. Okay. So what I'm going to do is kind of build this out. Just a reminder, how do we solve these games? So let's say I have the Republican candidate and I can run or not run these negative kind of attack ads against my opponent, right? We'll assume here we only have 2 candidates, like there's no Libertarian Party or anything like that. So here's kind of our normal form game matrix. And we said, if they both choose not to run these ads, nobody gains or loses any votes. If I don't run the ads, but my opponent does, they gain 1,000, I'm going to lose 3,000 votes. Similarly, if the Republican candidate runs the ads, they're on the left. We said the person on the left, their payoffs are always on the bottom left of these kind of visuals. So if they run negative ads, but the Democratic candidate doesn't, the Republican gains 1,000, the Democrat lost 3,000 votes. And if they both run these ads, maybe 1,000 people switch over to different sides, but there's now 2,000 people that don't vote on both sides. So each of them would lose 2,000 votes. Okay. So we said, how are we going to go through and solve these normal form games? So first, what I'm going to do is figure out what is person one's best response to each of the possible choices of person 2, or in this case, what should the Republican do if the Democrat runs negative attack ads? Well, if they run negative attack ads, they lose 2,000 votes. If they don't run negative attack ads, they lose 3,000. Which of those is better? Losing 2,000. If the Democratic candidate doesn't run negative ads and I do, I gain 1,000 votes. But if I don't gain any. What's better? Gaining 1,000 votes. So here I would say the Republican candidate has a what? Dominant strategy. No matter what the other person does, they always choose to run these negative attack ads. Now, solving this for person two, the Democratic candidate, if the Republican candidate runs negative ads, what should the Democratic candidate do? Well, losing 2,000 votes is better than losing 3,000. What if the Republican candidate doesn't run these ads? Well, gaining 1,000 is better than gaining nothing. So the Democratic candidate here also has a dominant strategy to run these negative attack ads. So what is our Nash equilibrium? Once again, not technical, right? But two circles in the same box. What that's really saying is we're both best responding to the other person's best response. So here I end up with this Nash equilibrium where we both run negative attack ads. Is this an example of a prisoner's dilemma? Yes, because if we could both agree not to run these negative ads, we would both neither gain or lose votes. Right? We'd both be better off. Okay? So this is an example of a prisoner's dilemma because we end up with a Nash equilibrium where both individuals could be better off from a different combination of strategy choices. But the incentives that existed to be the one person that run these negative ads pushed us towards this kind of prisoner's dilemma Nash equilibrium. So this is, I guess if we're thinking about this here, do these candidates really care? Well, the outcome of the election, if neither of us gains or loses votes, will be whatever it was going to be before. If we both lose 2,000 votes, the result of the election is going to be whatever it was before. So did he really care here? No. And I wouldn't kind of extend this, but to kind of connect some things, a more heuristic view of what we're doing in this class throughout the semester. Who is this a bad thing for? We now have 4,000 people who aren't voting. I think it's a good or a bad thing for our society. Bad, right? Essentially, these Nash equilibrium, even if the people, the players involved don't kind of care, like they're not hurt by it, who can be hurt? Society, or we have created negative externalities. So sometimes the Nash equilibrium would result in potentially not necessarily losses or gains for the players involved, but for people outside of this game or for society. Okay. So I set this up this way so that you can identify the Nash equilibrium. If we had the same payoffs, I still end up with the same exact Nash equilibrium where we both run these negative attack ads. But notice here, I actually flipped what player I put where. I flipped the decisions. It doesn't matter. When you're setting up these games, as long as you've gotten the payoffs written incorrect, it doesn't matter who is player one or player two or what order you put the decisions. If you solve it correctly, you would always end up with the same Nash equilibrium. So I think I had someone ask me after last class, like, how do I know who to put where? It ultimately doesn't matter, right? Once you've built this game, if you correctly kind of have these payoffs and correctly solve for the Nash equilibrium, doesn't matter what order, you'd always end up with the same Nash equilibrium. Okay. Any questions on this? So once again, kind of went through this last class, but just showing you a different example of how we would see kind of this prisoner's dilemma, maybe not in the context of markets, but a more political kind of example. Okay. Now, so this was kind of our result, right? It was a bad thing for society. So why might we see sometimes people cooperate? So like in this example, or in a kind of our duopoly, cartel, kind of coordinating our actions with pricing decisions example, we saw that people generally, we end up with these prisoner's dilemma where we break the agreement, right? So why might some people hold true to the agreement in practice, okay? So let's assume we have this set up. And I think in the slides, I put some bullet points in about what I'm about to say. But if we have two firms, and let's say they're setting prices, okay? So they can set the price, kind of both set a price of 100, in which case we're acting like a monopolist, and both of our profits, let's say, would be equal to $10 every year, just to make the numbers easy, right? If firm one sets a high price and firm two says, you know what, I'm going to undercut their price so that everybody wants to buy from me. Okay? Well, in the time period where they undercut the price, maybe this goes to I don't know. Firm one now, nobody buys from them, but they stay open, they're going to have some losses. Now, the firm that kind of charge a lower price, they're going to attract most of demand. Maybe they're able to kind of earn, I don't know, let's say here, what number do I want? Let's do 20. Okay. And then kind of the flip would be true if firm two set the lower, sorry, firm one set the lower price, firm two set the higher price. And then if they both kind of think they're going to undercut each other's prices, well, I only was gaining my profits before because I was the only one who sold at a lower price. So if we both simultaneously do this, maybe we both end up actually with losses. Okay. So if I set this game up for like, we're only doing this one time, I can end up with this Nash equilibrium where actually we both set kind of this lower price. Right? Now let's assume that we play this game 10 years in a row. Okay. So I could think about if I'm firm one, I can set this high price today, or I could set this low price today. Firm two kind of has this same decision, right? Now, I'll show you an example here where sometimes you could see this depicted not with kind of these diagonals, but I just use commas to separate the payoffs. So if we both set a high price, what will the total profits be over the next 10 years? Well, if we're earning $10 a year times 10 years, the payoffs with each firm would be 100 each. Now, if we both set this lower price, we lose 5 million every single year times 10 years. This would be what? Negative 50. Okay. Now, if I break the agreement in that first year, my profits go to 20. However, if we have this setup, we call it a tit for tat strategy. If you break the agreement once, do you think I'm ever going to trust you again? No. Right? You already broke this agreement. So on every period from there on out, I'm not going to trust you. And let's say we both set the perfectly competitive price. And from here on out, our profits are 0. Well, if I'm the one that broke the agreement, firm two, that means I would get 20 in that first time period when I broke the agreement, but 0 every other time period because now the other firm will never agree to work with me. So I would earn 20 over that 10-year time period. Now, the other firm, they're going to lose 10, right? But then from every period on out, we're back to kind of those, we're not even going to set up this agreement, right? We're just going to kind of both set this competitive price, earn 0 from every time period from there on out. Same kind of thing here over here. If firm one chooses the lower price, they gain 20 that first time period, but from there on out, 0 kind of profits, that perfectly competitive profit value. And then kind of here, firm one would lose 10 million that first time period, but from here on out, we kind of don't even try to make this agreement. We just set the perfectly competitive price. Okay. So I wouldn't give you something like this and expect you to construct this. I would just give you what these payoffs look like. Okay. So if I had this set up, so this is now where we have what we call repeated games. Okay. So we won't go super in depth into this, but I do want to show you how that can change our Nash equilibrium. So let's say firm two chooses to set a high price in that first time period. What should person one do, or firm one do? Sorry. Well, 100 is greater than 20, so they would choose that. If firm two sets a low price in that first time period, I'm never going to try to work with them again. What value would be higher here? Well, I might have trusted them that first time period, but I never will again, right? So losing 10 is better than losing 50. What about for firm two? Well, if firm one sets a high price that first time period, I continue to trust them. That's greater than 20, right? If I set a low price. If firm one sets a low price that first time period, which of the payoffs is better for firm two? I have negative 10. Losing 10 is better than losing 50. So what did I end up with here? My Nash equilibrium is that we both set a higher price or act like monopolists. So if we see this game repeated, we could go from the scenario we talked about last class, which is that we both break the agreement if we're only playing this game one time, to if we play it multiple time periods, maybe I stick or hold true to this agreement, because if I break it, yeah, there's short run gains, but I'm missing out on gains for the next 10 years because this company will never trust me again. essentially there's really high opportunity cost to breaking the agreement in that first time period. So if we repeat this game, sometimes we don't end up in that Nash equilibrium where we end up close to that perfectly competitive price. We see firms actually work together. And this is kind of like how OPEC operates. Most of the firms continue, they know we're going to keep playing this game, not for the next 10 years, but the next, as long as we keep using gasoline, who knows how long, right? And so we see that they're able to work together if we have this tit for tat strategy where as soon as you break the agreement, I never trust or want to work with you again. Okay? So there are things that could change our payoffs, which would then change our Nash equilibrium. Yeah, so is this an example of a prisoner's dilemma? So the definition of a prisoner's dilemma is there's no other outcome that provides both of them with higher payoffs. All of these result in lower payoffs, so this is not prisoner's dilemma, right? This actually results in the highest possible payoffs, this Nash equilibrium. Yep. Any questions on kind of how we went through and solved this? Okay. So we're kind of getting some more practice solving these normal form games. We kind of said, I'm going to try to get this so that I don't know why it does this sometimes, where it shows up kind of faint. There we go, right? So if we have this repeated game, potentially we end up with a different Nash equilibrium, okay? Now we'll work through one more normal form game example before we kind of switch gears and go to extensive form games, okay? So I kind of have this set up here. We're thinking about companies investing in the research and development. So we come up with these new innovative technologies or products. And, if we're both kind of putting money in, there's going to be some overlap. Like I come up with a similar product as you do, but we both might come up with like different products. And so maybe overall, if we can use each other's kind of innovation, these new products, we can increase our revenues by 15 million. But research and development costs money. So I had to spend 9 million to do that. Now, if only one of us puts money into research and development, well, now we only have the products that came from one firm. Maybe profits only increased by 10 million. Okay? I shouldn't say profits, sorry. Revenues increased by 10 million. The company that had to put money in had to pay these 9 million. But if I didn't put money into research and development and I can just back engineer what the other company did, I can get all those benefits without any of the additional costs. So if we were to kind of build this out, I've got two firms. I've got two decisions. I can invest in the R&D or I don't invest. If these are the all right, so we have Ford's kind of two best responses to what Toyota is doing. If Ford puts money in, what should Toyota do? Invest. If Ford puts money in, they should not invest. 10 is greater than 6. Right? If Ford doesn't invest, what should Toyota do? 1 is greater than 0. So if we went through and kind of selected both of the best responses for each firm to what the other firm is doing, we actually end up with an example here. And we kind of looked at this last class. I at least described it, thinking about we're running at each other. Do we go left and right? This is a chicken game. We don't always have to have one Nash equilibrium. We actually end up here with 2 Nash equilibrium. So we can have one Nash equilibrium. It can or cannot be an example of a prisoner's dilemma. We can also have multiple Nash equilibrium. We don't know what the result of this game will be, but whatever it is, we know it's going to be that only one firm invests. Okay. Any questions? Yeah. Huh? So I wouldn't ask you a question if it's a prisoner's dilemma with multiple equilibrium, but technically we could answer it outside of this class. So would this be an example of a prisoner's dilemma? So what's our definition? There's no other outcome where both people are better off. So if we were here, would both of them be better off? If we were up there, would both of them be better off simultaneously? No. So technically, we wouldn't have an example of prisoner's dilemma here. In the quiz and the exam, I would only ask you about prisoner's dilemma if there's one Nash equilibrium. Makes it a little bit easier. Okay. So let's take this result where we had kind of these payoffs, and let's think about something that we could do. Now I'm going to do firm one and firm two instead of Toyota Ford here, just to kind of, this could be any industry. So we'll kind of go here. We're going to invest or we're going to choose not to invest. Okay. So let's assume we had kind of similar payoffs. So we both invest 6. If we both don't invest, no new products. If I invest, but the other person doesn't, let's assume that we had that 1 million kind of dollars of profits. But now let's introduce something from the government. Right? What do we see often? I mentioned this last class. If I come up with a new product, I can get a patent. So we'll assume with a patent, I can't steal the other company or I can't reverse engineer it. Now, if I did, maybe let's say if there's a patent on a product and you use it, the government is going to charge you a fee, right? They're going to kind of penalize you for doing that, right? So let's say that cost was like -15 if you get caught stealing another company's products. Well, before my payoff here was 10, now it's going to be -5 because there's this huge cost that the government this huge fee that I get penalized because I stole this other company's kind of new product or their innovation. Same kind of idea would exist over here. If firm one invests, they get an additional $1 million. If I get caught stealing, I made 10, but then I have to pay this fee of -15. So if we went through and solved this game, and once again, I'll try to color code this here. If firm two chooses to invest, what should firm one do? Well, 6 is greater than -5. If firm two doesn't invest, what should firm one do? 1 is greater than 0. So now, after this kind of fee or penalize, the penalty from the government, I now see firm one has a dominant strategy. If we go back to the example we had in the slides earlier, what they did before without this penalty, their decision changed depending on what the other firm did. So here, neither firm had a dominant strategy. Once we introduced this idea of penalizing these firms for taking a product that had a patent on it, we now end up seeing firm one has a dominant strategy. Now, what about firm two? If firm one chooses to invest, firm two will choose to invest. If firm one doesn't invest, firm two would choose to invest as well. So we now end up with 2 dominant strategies and a Nash equilibrium, which is that both companies now invest. So before we had multiple equilibrium where only one company was investing. Now we end up with a equilibrium where both companies invest. So this potentially could be a good thing for some of the firms, right? Could be a bad thing for some, but who's definitely benefiting if all companies are putting money into research and development, coming up with new innovative products? Consumers. So if we kind of create some of these penalties to change the payoffs of this game, we might result in changing the Nash equilibrium so that we are now increasing total surplus for society. Or essentially, we're kind of creating positive externalities. Now, I won't ask you to tell me if there's positive or negative externalities from these games, but kind of trying to tie in all these things that we've talked about throughout the semester, seeing how they're all interrelated. Okay. So we can solve these normal form games. We can identify equilibrium. Sometimes there's one equilibrium. Sometimes there's multiple. Sometimes they're prisoner's dilemma examples. Sometimes they're not. Okay. Any questions on this idea before we keep moving here? We're okay with this? All right. So let me take a drink here real quick. So we kind of changed, right? If we penalize companies, we can change these Nash equilibrium potentially. So I've got one more example, and I'm not going to draw this one out, and I'll go through it relatively quickly because I wouldn't ever give you a game like this. I'll keep it limited to 2 strategy choices. But in practice, we can see like 3, 4, 5 different strategy choices. We would then go through this the same way. So if you've never played or you don't know this game of rock, paper, scissors, right? Usually, in grade school, you make it into things that are much more crude, all right? If we're making this decision simultaneously, we're making strategy choices. If I put down rock, you throw scissors, I win. If you also put rock, it's a tie, nobody wins. If I put rock, you put paper, you win, right? This is kind of how you win the game. So we could kind of depict this as if we both choose the same option, it's a tie. If I choose the option that beats you, I get a 1 because I win, -1 because you lose. Just what these payoffs represent. You could go through and identify the best response of each player, similar to how we've been doing these other games. Now here, I wanted to show this example because what can happen with some of these games? Do I have 2 circles in the same box anywhere here? No, right? So I actually end up with a game here where I have no Nash equilibrium. That is a possibility. And if you think about why in the context of like this example, if I throw rock and the other person throws paper, they win. So what would I do to best respond to their choice? I want to win, I would throw scissors. But then if we're at that outcome, what should person 1 do? Throw rock, right? Our best response to the other person's strategy choice would always change, right? So we never end up with this Nash equilibrium where we're both best responding to each other's best response. So when you look at these games, 3 possibilities. 1 equilibrium, multiple equilibrium, sometimes no equilibrium. Okay? So that is a possibility. Any questions here? Right? So if we don't have any equilibrium, it's basically a guessing game for what the outcome is going to be. Right? We don't really know. Okay? So we're now going to transition from thinking about these normal form games to what we call extensive form games. Okay? So extensive form games are sequential decision making. So all these other examples, we're assuming the 2 players involved made their strategy choice at the exact same time. So the idea of like rock, paper, scissors, we make the decision at the same time. Setting prices for today, we make decisions at the beginning of the day at the same time. Right? Like gas companies, right? They go up in the morning, choose what the price is going to be. Okay? So the way that we're going to build these out when we have sequential decision, it's person 1 makes their decision, and then person 2 gets to observe that and make their decision second. So instead of these normal form game matrices, we're going to set this up as a decision tree. We're then going to use something called backward induction, which is the person who gets to go second. We're going to figure out what their best responses are. And then given those best responses, what should player 1 do? Okay. So this will make a little more sense, I think, as we work through these. I've got a goofy example to just kind of set this up, and we'll think about something that looks a little more realistic in the context of like markets. So this old, cartoon, Charlie Brown, right? One of the running gags of the cartoon is that Charlie Brown, Lucy's holding this football. He goes to run to try to kick it. And what does she always do? Pull it away at the last second. So why is this funny, right? Because if we were to solve this as an extensive form game, Charlie Brown is making the decision first to choose if I'm going to run and try to kick that football, or I could just walk away. Those are his 2 decisions. If he walks away, Lucy doesn't really get a decision, right? She can't pull the football away or keep it there because he's not going to try to kick it. If he tries to kick it, accepts this offer, right? She then has a decision to make, which is, do I let him kick the football? So she sees that he's running, right? She gets to observe his strategy choice. She could let him kick it, or she could pull it away at the last second. If he kicks it, she's not amused by this. Her utility is essentially 0, right? If she pulls away at the last second, she's amused. She gets positive utility. Now, if she pulls away at the last second, Charlie pulls down, negative utility. If he kicks it, he feels good about this. He gets positive utility. So we're going to first solve for the person going second who loses. Should she pull the football away or should she not? Well, where is she better off? She gets amusement from pulling that football away, right? So we would kind of think about that's her optimal strategy. Now, knowing this, knowing that that's her incentives that exist, we're going to make the decision for the person going first. So Charlie Brown knows if he walks away, nothing's going to happen. He gets no enjoyment, but he also doesn't fall down. So his utility is essentially 0. If he runs towards Lucy and tries to kick the football, he knows she is always going to pull it away. Now, that's her optimal decision or her best response to him doing that. Well, if she pulls away, he knows he's going to fall down. He knows she would never choose this option. So essentially, he would like cross this out. This will never be something that happens. So his decision is really, do I run and try to kick the football, knowing Lucy always pulls it away? or do I just walk away? Well, negative utility is worse than zero utility. So the optimal decision for him really should be to reject this offer to kick the football and walk away. This is why it's funny that he always chooses to try to kick the football, because he always ends up with a lower payout. So here we would kind of have this Nash equilibrium, which should be that Charlie Brown rejects this offer. But if he did accept it, we know that Lucy would pull it away. Right? So we end up with this outcome where he should reject the offer. We'll look at something that's a little bit more realistic kind of in the context of markets. Okay. So let's say I have this set up, and let's show you here. I've kind of got this kind of selected here. I'll kind of walk through this. Well, I'll write this out real quick because I think it'll help. You can work through it in the slides, but I think we've got enough time where I think it's more helpful if I write this out. So we've got, let's say we've got an existing firm and they're currently a monopolist. They can set this monopoly price or they can set a more competitive price, right? We can think about a second firm who is choosing whether or not to enter or not enter the market, right? So given what the existing firm or the current monopolist chooses to do, they then get to make a choice second. So they see the price that that firm set. They get to then make their decision, do I join this market or not? If they enter the market, they can undercut the monopolist price. So the monopolist profits actually become negative, and kind of firm two's profits would be positive. If they choose not to enter the market, the monopoly still gets to enjoy positive monopoly profits, and firm two, they didn't join the market, they're producing nothing, they have no cost, no revenue, so their profits are zero. If the monopolist sets a competitive price and firm two enters, well, they can't undercut that price because at the competitive price, profits might be equal to zero. So if they now join that market, now demand gets split, but both firms are choosing that kind of perfectly competitive price. Both firms' profits in that scenario would actually be negative. Okay? So at this lower price, before the monopolist profits would have been zero, but now they're splitting demand. Each firm is going to get half the demand. We have negative profits. Now, if firm two chooses to stay out, the monopolist was setting that perfectly competitive price, earning profits of zero. They're no longer splitting demand. Profits stay the same. And the firm thinking about joining, they didn't join, so their profits are zero. It's the exact same payoffs I had written on the slides. It just makes it a little bit easier for me to show you how to solve this. Okay. So we said we're going to use backward induction. So we think about what will firm two do in response to what firm one is going to do. So if firm one, the existing monopolist, chooses this higher monopoly price, once again, similar to the normal form games, we put person one's payoffs on the left, person two's payoffs on the right. Makes it nice and easy. So what should firm two do if the existing firm sets a higher price? Well, what's better, positive profits or zero? Positive. If the existing firm sets a more perfectly competitive price, what should firm two do? What's better, negative profits or zero? Zero. So the way that I would solve these is we now know firm two's best response to each of the possible choices of firm one. We know that these will never be outcomes. As we know, firm two will always choose to do this. That's their best response. So the second step is knowing this. So what we assume in all these extensive form games is that everybody knows what the kind of payoffs of this game will be. So firm one knows what firm two's payoffs will be, and so it can identify what firm two's best responses will be to both of its possible strategy choices. So if the monopolist chooses to set a high price, the monopoly price, their profits will be negative. That firm would choose to enter. If they set a more perfectly competitive price, firm two will not enter and their profits are zero. What's better for the monopolist? Zero economic profits. So we end up with this kind of Nash equilibrium, which is that firm two does not enter the market and firm one, the existing monopolist, chooses to set a more perfectly competitive price. Right? So this is a bad thing for the monopolist. Who is it a good thing for? Society. Right? So we get kind of a similar result as the simultaneous game here, which is we end up seeing that a price closer to that perfectly competitive price. Right? Now, it's a little bit different in that we don't have two firms anymore, right? So we only have kind of one firm, but they still kind of end up getting down to that perfectly competitive price. If we have no barriers to entry, right? That second firm can choose to enter or not enter the market. Any questions on this idea before we keep moving? Okay. So I solved this one in a similar way, but if it's all a little bit of individual preference. Instead of selecting those payoffs, you can select like what strategy choices they're choosing, and you still result in the same Nash equilibrium. It's just, I don't know. For me, it makes it easier to see what that Nash equilibrium is if I select the payoffs as kind of the optimal strategy choices, but ultimately it doesn't matter. Whatever makes the most sense for you. Okay. Any questions on this idea before we keep moving? All right, so we had an example with one Nash equilibrium. I drew this out for you, kind of just seeing it, how you would kind of solve through it here. So we'll kind of keep moving. Where are we at in time? All right, perfect. So you could do a similar thing with this rock, paper, scissors. So I will keep things in this class limited to similar to the normal form games, 2 decisions. Right? So you would never have something that looks like this because I now have 3 decisions of every turn. Now, if I had my game set up this way, right, we can think real quick. Once again, I'll draw this out. We could do this on the slides, but I think we have time. So I think it's worthwhile to see how you would solve this or how I would go about solving it if I was writing this out. So I've got rock, paper, scissors, person 2. If this was not a simultaneous, but a sequential game, well, before we even go through this intuitively, if we're playing rock, paper, scissors, and I get to go second, who's always going to win? Person going second. Because whatever you throw, I know what to play to beat you, right? But we could really kind of build this out as an extensive form game, right? So given the other person, I now have 3 choices to make. So if we both put rock, payoffs are what? 0. Paper beats rock, so person 2 wins, person 1 loses. If I play scissors as person 2, I lose, person 1 wins. Oh, sorry, I put rock here. This should be a P, right? I was writing quickly. So if we both put paper, nobody wins. Scissors, nobody wins. Rock, person 2 would actually lose. We could kind of write in all these payoffs. So what? Rock beats scissors. So 1, -1, 1, -1. Okay? So I'm just writing all these payoffs like I had them in the slides. 1 representing I win, -1 I lose, 0 it's a tie. So I would go through, first solve this for the person going second. So if player 1 chooses rock, what should player 2 do? Well, 1 is the highest payoff. If player 1 chooses paper, what should person 2 do? Play scissors, that's the highest payoff. Similar kind of idea. I now have person 2's best responses. So what I would do here is I've still got a lot of options looking at, but if player 1 knows the payoffs of this game, it knows person 2 will never choose these options. It can identify person 2's best responses to each of my, as player 1's, possible strategy choices. So if I throw rock, I know I'm going to lose. If I play paper, I know I'm going to lose. If I play scissors, I know I'm going to lose. What do I actually end up with if the game of rock, paper, scissors is a sequential game? Multiple Nash equilibrium, right? Because person 1, I don't care what I play. I know person 2 can always beat me. right? If they get to go second. So this is what we call a second mover advantage. Person two is always going to win. Now, we don't know what outcome we're going to end up in. It's kind of completely random, just like I don't really care as person one when I play, but we know we're always going to end up with an equilibrium here where person one loses, person two wins. So just like normal form simultaneous decision games, we can have one equilibrium, like in our firm example. We can have multiple equilibrium. Okay. Any questions on this idea before I keep moving? So if I'm solving these, I just think it helps. Once you identify the second person's best responses, cross out the decisions you know they won't make. Because now as firm one, these are the payoffs that I'm actually comparing. Okay? Before we go back to the slide, any questions here? Okay. So we have this example where we have multiple equilibrium. Okay. So we're next going to think about a couple interesting scenarios, or sorry, examples that I think hopefully push us a little bit further than maybe what I would expect you to know, but I'll kind of put them in the context of like what I would give you on a quiz or an exam. So let's say I have this setup and they run these. So there's an economic experiment lab here. I probably should have brought the link in here. Maybe I'll post it up in an announcement. So you can sign up to do these experiments and like they pay you like a certain base fee for showing up and participating. And then based off your performance, you can earn more money. Right? So they run them here in the economics department, and they run them like all these different universities. And they see, are people making optimal decisions in these games, or are they not making the correct decisions based off of what the theory predicts? So there's this sharing example where they give them like $100 and say, you can offer the other person any amount of this $100 in $1 increments, and then they get to decide, do they accept or reject this offer? If they accept, you get the split that you offered. If they reject, you both get nothing. So this is the idea. So I give them $100. They go to the second person and say, I'm going to give you $20 and I'm going to keep 80. Do you accept it? Person two then says, yes, I accept it. Person one gets to keep 80. Person two gets to keep 20. Or if they reject it, they both get 0. Now they can do this in $1 increments. So the way that we would set this up in a sequential game, well, person one is making the offer first, right? So if I think about person one here, and usually in these games, it makes it a little more complicated if I let them offer them nothing, and that doesn't really make sense. So the lowest possible amount they could offer the other person is $1. In which case, person two then gets to choose, do I accept or reject this offer? So I'm just shorthanding here. This would be accept and reject. If they accept the offer, person one, their payoffs are on the left. They get to keep 99. Person two only gets $1. If they reject, they both get nothing. Person one could then also offer person two $2, right? Person two then gets to choose, do I accept or reject this offer? So if they accept, they get to keep 2. Person one gets to keep the remaining 98. If they reject, they both get nothing. So what amount should person one offer person two? Well, if we both know the payoffs of this game, I would kind of solve this backward induction. Start at the bottom of the tree. If person one offers person two $1, what will person two do? Accept. If person one offers them $2, what will person two do? Accept. So knowing this, person one says, I will never see person two reject my offer in this case. So if I give them $1, I get offer them $1, I get 99. If I offer them $2, I get to keep 98. Which of those is better for person one? 99. So we end up with this Nash, and really I could extend this because they could offer them $3, $4, $5. But no matter which of these I look at, it's always better for person one. I know that person two is always going to accept my offer. I want to offer them the lowest possible amount. this would be our Nash equilibrium. Okay. Any questions on that idea? I'm going to change things a little bit here to kind of see to better represent what we see play out in practice. Okay. So this would be like, I'd only give you kind of a 2-decision tree. I wouldn't expect you to do like every possible kind of dollar amount here, but the same concept would apply. It always results in the Nash equilibrium being the lowest possible amount person one can offer them. Now, if instead I had kind of this similar setup, so here's person one's choices, and then person two gets to choose, do I accept or reject this offer? Mm-hmm. So same setup. If they reject, or sorry, hold off on this. So let's say they accept the offer, right? Player one gets 99, right? And, you know, let's assume I get to keep this $1 over here, 98 and 2, nothing has changed. Okay. Now, if this was going to occur in real life, if you know that the person who's offering you $1 out of 100, would you accept that? Why? Because screw them. Why you offered me $1 when you could have even offered me a 50-50 even split? So there's something that we're not factoring in. Yes, money, dollars matter, but when consumer or individuals make decisions, they make it based off of utility. If I value spiting the other person, right? So maybe like the value I get from seeing them get nothing because they gave me this really bad offer. Maybe now if I reject, person one gets nothing, but I actually get the satisfaction of seeing them get nothing, right? So that would kind of occur here as well, because they offer me such a low amount. I want to see them, I want to reject this offer. So what would kind of occur here? Now, if we go through and kind of solve this, for person two, they're making the decision second, so we'll solve it for them first. If they're offered $1, what are they going to do? Reject that offer. Having the $1 doesn't compensate for the fact that I now see the other person get to keep 99. I value making sure they get nothing way more than getting $1. And then if they offered me $2, what is my best response? Still to reject that offer. Okay. Knowing this, what is person one going to do? Well, they know that these are never possibilities, right? So here, kind of I'm comparing 0 to 0. I'm not going to offer them 1 or 2. Or I could offer them 1. It doesn't matter to me. My payoffs are the same. Okay. So it looks like I kind of have multiple equilibrium here. That can happen with these sequential form games as well, right? Kind of sequential decision-making extensive form games. Okay. Now, I didn't build this out completely, right? Because technically I would kind of keep on adding things in here. But essentially, where would I kind of stop with this idea? Where would person two start to accept this offer? Not 50-50, because if I value my spite at 10, as soon as they offer me 11, that's a little bit better. Now, if I really care about equity and I value like seeing this even split, then yes, I won't accept it until it gets up to that 50-50 amount. All right. But in practice, we don't see people go quite that far. I mean, I want to get an equal split, but at the same time, they start offering me $20, $30, still 20 or 30, right? It's over the amount that I value spiting the other person. Okay. But I would never kind of give you anything more than just a 2-decision game, right? But we could kind of build this out, in which case we would see where does the person start to accept the offer at whatever value is just above how much they value spite, essentially. Okay. And this is what we see play out in these economics experiments. Okay. Any questions on this before we keep moving here?
If like actual economic experiments, what if like the internal person and value and the type of person, like how is actually valued?
Yeah, right. So when we actually start to look at these models, the actual, like what I'm actually painting in the lab would actually be a theory that is more complicated than what we would do in this class, which is I said, I assume in these games that everybody knows the payoffs. I don't really know how much somebody values spike, right? So what ends up being true is we have to have a more complicated model to determine what this is, because I might have an idea of how much they value spike, but I don't know the exact value. So what might we see people do in practice? Err on the side of caution. Go closer to that 50-50 split if I don't truly know how much someone values equity in this example. Yep. And they usually don't play with $100. Usually it's like 10, but it's the same idea, right? Okay. So that leaves us thinking about. So I had this kind of sharing example, right? So we'll kind of go here. I've got this quiz. I'm going to make sure I adjust the time here. And I think the number is 82.05. So we'll make sure that gets you into the quiz. But 82.05 should be. Is that working? Anyone want to verify with me? I can check it here real quick, but yeah, 82.05 will get you into that quiz. We have it set to be due at 10:40. We'll kind of talk through this. Okay. So let's say I had a setup that looks something like this. Okay. Here are a lot of murmurings. Are we getting into this okay? Yes, no, yes. 82.05. Okay. So if I have a setup that looks like this, and I've got two firms. So we're going to go back to that idea of like, do I invest or not invest in the research and development? So before, when we didn't have any penalties from the government, we had an example where we actually had multiple equilibrium if we were making this decision simultaneously. What if firms make this decision sequentially? One firm chooses to invest in research and development. I then get to kind of make my choice second. So how do I solve this game? I first determine what the person going second or firm two's decision is for both of the possible choices of firm one. So if firm one chooses to invest, what will firm two choose to do? And once again, I'm not trying to trick you. Firm one, I'm always going to put this, or whoever gets it first, I kind of make sure those numbers line up. Like firm one, they go first. Firm two, they go second. Firm one's payoffs, just like the normal form games, are always on the left. Person two, or firm two's, their payoffs always going to the right. So if firm one invests, what should firm two do? Yeah, if they invest, they get 50 million. If they don't, they get 60 million. This is the idea. There's no patents, there's no legal fees from the government. I can just steal what they came up with. So they're going to choose the higher payoff, which is the strategy choice of not investing. So I said, what would be the next thing you would do if we were doing this by hand? We know they're never going to invest in this scenario. I would just scribble this out. We know that this won't occur. We know firm two will never choose to invest on this branch of the decision tree. We then go over here. What would firm two's best response be if firm one chooses not to invest? Well, losing 20 is worse than gaining 10. So they're going to choose to not invest. Right? So I would circle that kind of decision or that payoff. Once again, I know that firm two would never choose to do this, so I scribbled out as a possible outcome. So I figured out firm two's best responses. I then go back and say, what is firm? I can get this all to be on the same thing. There we go. What is firm one going to do knowing these payoffs exist? Well, they know if they invest, firm two will always not invest, and they end up losing 20 million. They know if they don't invest, firm two will always choose not to invest, and they end up making 10 million. Which of those is better for firm one? 10 million. Right? Gaining 10 is better than losing 20. Right? So they would choose kind of this payoff, which comes from the strategy choice of not investing. Our Nash equilibrium would be down here, where both these firms choose to not invest. So here we've got kind of one Nash equilibrium, which is both firms don't invest. Unlike when it was a simultaneous decision game, we said without penalties from the government, we ended up with multiple equilibrium where one firm was investing, one wasn't. So when we look at these, the payoffs matter, right? But also whether or not the decisions are simultaneous or sequential can change the outcomes of these games or change the equilibriums of these games. Okay. Any questions on this idea? So I just worked through it. If you're paying attention, we should know this Nash equilibrium, which is we end up with both firms not investing. Okay. Any questions here before I keep moving? Okay with this? So once again, if I'm writing these out by hand, I think that idea of like scribbling out. So you make firm two's choices first, scribble out what you know they won't do. Then knowing the kind of outcome of each decision for firm one, figure out what provides the highest payoff for that person going first or firm one in this example. Okay. So one thing I want to point out here, what is helpful about scribbling these out is because if I did choose to not invest, it might look like, oh, I could make $60 million as firm one. Well, yeah, but I know that firm two would never choose to do this, so I'm really only ever going to make it, right? So that's where kind of scribbling out these outcomes you know won't happen because of firm two's decision, who you figure out their best response first. That's going to help you kind of arrive at the correct answer. So I'm going to give you the next couple minutes. There's no right or wrong answers here, but just for the sake of humoring me and also to kind of make a point, and I'll actually think through what these types of games are. Let's say I ask you all to guess a number between 0 and 100. So the way you would win this game, let's say if you get this correct, I'll give you an A class. Not that I actually do that, but let's say that's the inception. I can't do that. I'd be like, they kicked me out of this university, right? So you're all going to guess a number between 0 and 100. The way you would win this game is if you guess half of the class's average guess, you would win. Okay. So I'll give you another minute or two. Think through this, right? There's no correct response. You're just going to guess the number that you believe will be half of the class average. And the numbers that the class can guess is only numbers between 0 and 100. Yes, you're all trying to guess half of the class average. Okay. So I'll give you a minute or two. I'll then prompt you to make sure you submit this before the due date, and then we'll kind of talk through this. Okay. Okay, so make sure you've got your answers in. Hit submit. It's due at 10:40, so we've got a minute. Make sure you're getting this submitted now. Okay, so everybody's got this submitted. Okay. All right, so sorry, I didn't mean to choose this to blank. I meant to choose this over here. All right, so if everybody randomly guessed a number between 0 and 100, what would the average be? 50. Now, if you're trying to guess half the class's average, if everyone guessed randomly, the average is 50, what number should you guess? 25. That would mean you win, right? Now, so sorry. So we have this is going to be the scenario. So if everybody thinks that, if everybody guesses 25, what's the average actually? So if I guess 25 and everyone else does 2, nobody wins because the correct answer would be 12 and a half. Now, if I guess 12 and a half and everybody else guessed 25, it wouldn't be quite the average of the class, but it'd be the closest, right? So in that case, I would win, class loses. If I guess 25 and the rest of the class guesses 12 and a half, I lose. Now, technically here, nobody wins, right? Because if we all guess the rest of the class is 12 and a half, nobody guessed half the average. If everybody guesses half the average, who wins? Nobody, right? So we can kind of go through, solve this quickly. What should person 1 do? What should person 1 do? What should the rest of the class or person 2 do? Well, we could actually end up with a scenario here, right? Where we end up with this Nash equilibrium where every person, if they're making decisions for themselves to try to win this game, they should always guess the lower value. But if everybody has that incentive, right? What is our Nash equilibrium? Everybody guesses the next lowest value, in which case we have more options we could choose, which is everybody guesses 12 and a half. What should you have actually guessed? 6.25. But then if everybody guesses 6.5, what should you have actually, or 6.25, you should have actually guessed what? 3.12. This process would exist until everybody guesses what value? 0. If everybody guesses 0, who would win? What's half of 0? 0. Everybody should win this game. Now, the problem is what we have in practice, and they run these in the labs, and what they find is that people are what we call, and this kind of sounds derogatory, it's not meant to be, but this is the economic literature. We call people level K type thinkers, right? So if you thought through this and we're like, you know what? Everybody's going to guess, they random, it was 50, I should guess 25. That's a level 0 type thinker. Level 1 type thinker would be, well, I know everybody's going to guess 25, so I should guess 12. Level 2 or level 1. And if everyone gets 12 and a half, 6, level 3, level 4, level 5. If you're a level infinite type thinker, you would have guessed 0. All right. So I'm looking at the class average here. It was 10.7, right? So we didn't quite get to what that Nash equilibrium should be. But the reason why this is an interesting example is because even though we have these theories and they predict that these Nash equilibriums should be 0, people don't get things correct, right? Sometimes people don't actually behave the same way our theory predicts, which means we need to update our theory, which is what economists did when running these in the lab. They realized people aren't actually able to do or actually able to understand what their best decision should be, and that some people stop at a level of thinking that they didn't really need to continue to go down, right? So this gives us a better idea. How can we update our theories that capture the fact that not everybody has the same level of thinking, that there's actually a distribution? And then it gets much more complicated. The solutions to these games become much more complicated. But I thought that's an interesting example that we can start to think through. Once again, tying it. They run these in like a lab in these economics experiments. So these are the type of things that you would kind of be asked to do. And then based off of like how close you were, you might get a different payoff kind of in these experiments. So given this, getting towards the end of the semester, so I try to personalize myself so you don't hate me too much. So this is my son the other day. It was nice and beautiful out, just kind of chilling. So maybe that, I don't know, puts a smile on your face. The other thing, on the way out, I told a student I would do this, so I don't know what course this is for, but they have a little survey where they're trying to gather data to kind of help them out. If you want to, on the way out, catch a picture of this QR code, kind of fill that out for them. Otherwise, Canvas discussion due at the end of the day tomorrow. Have a fun, safe weekend. I will see you Tuesday.
Hey, I have a question. So, uh, I heard, or like, I've been doing the examples and stuff, and I thought I like noticed something. And I was just like trying to see if it's right. So, if there's two, what is it, dominant strategies, does that always guarantee there's one Nash equilibrium? If there's no dominant strategies, it could either be none or many. And if there's one dominant strategy, or wait, there can't even be just one, can there?
There can be. You have one dominant strategy, one's not. So there has to be two if I have why am I blanking the word? If I have equal payoffs for both sides, symmetric payoffs, sorry. Then yes, if one person has a dominant strategy, the other person does. You'll see in the games like when we work through like the work hard shirk example, payoffs are not always like the same for both people. So you can end up with one dominant strategy and one not. If that
Can
ever
get to one Nash?
yes.
Okay.
All right. So you can still end up with, even if you don't have dominant strategy, you can still have one Nash equilibrium.
Okay.
If you don't have dominant strategies, you can end up with multiple, but you could also end up with none. So I wouldn't memorize kind of all of those possibilities. I would make sure I can kind of work through and solve these. Although the one that, if you want to memorize it, that always works. Two dominant strategies,
One Nash.
you always want Nash equilibrium.
Okay. Perfect.
Now, whether or not it's a prisoner's dilemma,
yeah,
depends on the payoffs. But two dominant strategies, you'll always have one Nash equilibrium.
perfect. Thank you.
Okay.
So Lance, so I had like I was doing the quiz and I had the answers put in already,
Mhm.
and I thought that it would automatically submit at 10:40 because I was listening to your explanation and I like forgot to submit it.
Okay, so this is why I always try to prompt you guys to make sure you're hitting submit, right?
Yes,
So what's your name?
Alan Tom, ALAM,
So Alan,
last name TA.
I can find it from there. So I'll throw this with one caveat because I obviously can't see if everybody's here. So I've
Right.
had students who try to come in at the end. As long as I can see that you opened the quiz before that due date and
Right.
didn't just spend 30 seconds on it, I'll adjust.
Yeah.
Okay.
That's what it is.
Yep.
I have a question regarding questions with monopolies where you're looking at the demand curve equation
Mhm.
and you're given marginal cost.
Mhm.
Do you have a second?
Mhm.
So yesterday I was working through the like final exam practice,
Yeah.
had one of those questions, and I remembered in class you using the derivative to find it. So you take the marginal revenue equals marginal cost, marginal revenue equals the derivative of total revenue. And so through that you can find the answer. But you could also just multiply the slope of the equation by 2
Yeah.
to find it. So do you recommend using the derivative or just taking the shortcut?
So I'm going to keep everything linear. So the derivative of a linear demand curve will always just be twice as steep. In practice, if you didn't have a linear demand curve, there you'd actually have to take the derivative. So I wouldn't worry about it. Your marginal revenue curve, I always explain it this way for this level of the class, right? It starts out at the same point as demand, so it has the same intercept, but it's going to be twice as steep, always.
So just stick to the shortcut.
I mean, usually that makes more sense. But if people are really mathematically minded, sometimes they like to take the derivative and that proves to them, oh yeah, same intercept, but twice as steep. But that'll always be the case.
All right.
Okay.
Thank you.
Yeah.
So I had a quick question. Is there one more week of material that we're learning, or is this all of the material?
Nope. So we've got one more week
Okay.
of material.
Because I wanted to get started on those practice exams that he was just talking about.
Yep. So you can, you can start on them
Mhm.
because it'll be about 3/4 of the questions you could get through.
Okay.
And they're written in like the order in which we cover things. So, I don't remember how many questions exactly I put in there. If there's like 30, you could probably get through like the first 23,
Okay.
right? Or 22 at this point. So you can start making a pretty good dent. The stuff that's at the end, the last 6 or 7 questions are probably going to be what we cover next week, which is monopolistic competition.
Okay.
Does that
Yeah, that covers it.
Okay.
Thank you so much.
Yeah, no
Uh,
worries.
So do you recommend